Okay, we started talking about organic chemistry last time. So a reminder that there are different types of organic compounds, but they really do all sort of come back, as we've been talking about, to what are referred to as alkanes. Alkanes are really the simplest sort of organic compounds you could have. Their sort of functional group is really the carbon-carbon single bond. And it's really important, as we talked about last time, that you get a handle on sort of the first 10 alkane names, because everything really revolves around those names. So again, one carbon has 4 hydrogens, will be methane. They do have a general form of CnH2n plus 2, n being the number of carbons there are. C2H6 would be ethane. C3H8 would be propane. C4H10 would be butane. Then they kind of go with the normal sort of prefixes, starting with 5, which would be pentane, and then hexane, heptane, octane, nonane, and decane as you finish out the first 10. Now, they're really important because really everything does come back to those first 10 names. We just changed a little bit about the name to sort of fit the other types of organic chemistry type groups. Pretty much all organic chemistry groups have a functional group, and a functional group is the important part of that organic compound. It really is the part that makes it, for example, a certain type of organic molecule. It's also usually the part where pretty much all reactions sort of take place, is sort of at that functional group. It's sort of really the most important thing. We got into naming there towards the end. The IUPAC way of naming is usually the more formal way of naming. That's the International Union of Pure and Applied Chemistry. And when we do this, as we talked about, we did a number of examples. I think we want to look for the longest continuous carbon chain. Remember, as we saw in a few of those examples, it may not always be the straightest. May go up and over, or may go up and down, or may go up and over, and all that kind of stuff. But you remember, as we talked about, you do want to sort of try all of your options and try to find the longest continuous carbon chain. The only real rule is you can't go backwards. So once you start in sort of one direction, you keep going until you hit a dead end, and you just can't sort of backtrack. Once you do that, that really should match one of those 10 alkane names, and that becomes really kind of the base of your name. So that whatever may match. So for example, if it was obviously 3 carbons, it would match propane, and propane becomes really the kind of the base of your name. Anything that's not part of the longest continuous chain are what are referred to as groups. And these groups, if they are carbon-based groups, they are what are referred to as alkyl groups. And the difference between sort of the alkane and the alkyl group is, as we talked about, it pretty much has one less hydrogen. And the purpose of why it has one less hydrogen is that it will allow it to bond to the main chain without having too many bonds. So remember, carbon can only have 4 bonds. So we can't just stick the whole alkane on there. Otherwise, that carbon will end up with too many bonds. So they typically, these groups are guys that have one less hydrogen that allows it to connect in. They're also named the same way. So, you know, we saw a number of these sort of CH3 groups. And once again, this one carbon is based off of methane. We drop the last part of methane, and because it's a group, it has one less hydrogen. It's a methyl group, YL at the end. Just like if you had a 2 carbon group, it would be an ethyl group and propyl group and so forth. If you go down all the way there, pentyl group, if you had 5 carbons with one less hydrogen, you just put YL. Other common group names do revolve around the halogens. And those halogens are named like bromol for bromine, chloral for chlorine, fluoral for fluorine, iodo for iodine. So those are the way you kind of name those halogens type of groups. We will see today, and we talked maybe a little bit about it last time, there are a few groups that have sort of historical names that are still sort of used today, and we'll sometimes name those. So once you find the groups, they're attached. Once you have the longest carbon chain, remember you want to number the longest chain. And in the case of alkanes, we want to number the longest chain to give the groups the smaller numbers. So the groups here get the priority and it gets the smaller numbers. And remember that once you sort of choose which way you want to kind of number it, you do have to stick with that no matter how many groups are attached. That's the way you chose the number. And it really is as simple as, like, 2 is less than 3, basically, depending on which way you go. Once you have all that, we want to put our groups in alphabetical order. And that's regardless of prefix. And what I mean by prefix is, again, if we had perhaps 2 methyl groups in a compound, you would put dimethyl in front of the methyl. So it'd be dimethyl or trimethyl if you had 3 guys. And again, that is in the entire compound, not necessarily on the same carbon. And then we get the base of the name, and we do give the numbers where all these groups are located. And whenever we write it, again, if we have a number going into a letter, we use a dash, or even a letter that goes into a number, we use a dash between them. And if you have 2 numbers, then we use a parentheses around them. We do want to put the groups in alphabetical order regardless of numbers. So even if a group has a higher number, but alphabetically it should come first, it still comes first, even though the number is higher. And we put them in alphabetical order. Any questions on any of that stuff there we were talking about last time, I think? Okay, so let us continue on. I've sort of jumped a little ahead, so we'll continue. I think about here is where we kind of laid up. Cycloalkanes, as we talked about, are alkanes where basically they kind of close in on each other. The back end and the front end of the ring are the structure. And when it does that, remember, as we talked about, pretty much in organic chemistry, anytime you make a bond, you sort of will sacrifice 2 hydrogens to make that bond so that no carbon has too many bonds to it. Usually a hydrogen from each side is sort of sacrificed. So cycloalkanes have the general form of CnH2n. They don't have the +2 part because they have closed up the ring, and we'll make that. The simplest cycloalkane you could get, well, it does come from propane here. And from propane, what happens is the 3 carbons sort of close up on each other into a ring structure here, which is basically a triangle. And that is 3 carbons, and each of these carbons have a hydrogen coming off of them, or actually 2 hydrogens. So that gives us C3H6 as our guy there. This would be, again, most of these cycloalkanes are written in line structure, so just kind of look like that. This would be sort of the condensed version of it. I'll spit that out, I think. Will look something like that when you draw it. When we name cycloalkanes, it's pretty much you just put cyclo in front of the name. So this is 3 carbons, which is propane. So this would be cyclopropane. So you basically just add cyclo in front of it if it is this sort of ring type structure where they come together. If we had something like our other shapes, we have something like this, which is a square, which is basically 1, 2, 3, and 4 carbons, which is butane. So this would be cyclobutane. We also have this guy here, which is 5 carbons, which is based off of pentane. This would be cyclopentane. And obviously we have this guy here, which is 6 carbons. And this would be based off of hexane, which makes it cyclohexane. So typically speaking, a lot of times these cycloalkanes are drawn a lot of times in line structure, just, makes it a little bit cleaner of a picture. But here again is a table from your book. And again, that is sort of the expanded structure. And obviously those would be the line structure. So if we have any of these guys, we basically just name them. Now, if they happen to have something attached to them, so for example, if we had our square with a line. So what this would mean is the main part of this compound is the square. And obviously that is 4 carbons as we see to the right, which would make it cyclobutane. But we do have something hanging off of it here. And hanging off of it, we have this guy right here, which is basically just a line that's coming off. And remember, sort of in line structure, if it's just a line with nothing at the end of it, it is a methyl group. It's a carbon with 3 hydrogens at the end of it. And what we would name this is we just put it in front. This would be methyl cyclobutane. You do not need to give the number as to where that group is located because there is only one group on that square, which means if you drew it that way, that would be carbon number 1 where it's located. If you drew this guy this way, this would then be carbon number 1. So it doesn't really matter. So when there's only one group on it, it's sometimes referred to as being mono-substituted. You do not need the number because wherever that group is located, it's assumed to be carbon number 1. When you do get, though, maybe a couple groups that are attached, you do need to give the numbers. And again, you would want to do sort of the smaller numbering. So if we had something like this, and we'll do that, and we'll do, say, this. Now, in this case here, we do have a couple of things that are attached. So we would still follow the same sort of rules here. The big part is obviously our cycloalkane here, which is 6. So the base of this name, once again, would be, let's write it here, I think, cyclohexane. We do have a group here, which is a methyl. And we have a group here, which is a bromol. And in this case, we do need to number. Now, we have a couple of different ways that we could go about numbering this guy. And we want to think about sort of what we want to do in terms of the name. We do know that name-wise, right, we're going to put our groups in alphabetical order. So which one should come first? The bromo should come first, right? So when we go to name it, we probably want to start there and give that guy the lower number since, it's going to come first in the alphabetical order. So we would probably want to call this carbon where that guy is located as carbon number 1. We then have really 2 options to number. We could go clockwise, which would be carbon 2 and carbon 3, carbon 4, carbon 5, and carbon 6. And that would give us groups at carbon 1 and 3 if we went clockwise. Now, if we decided to go counterclockwise, that would be carbon 1, that would be carbon 2, that would be carbon 3, that would be carbon 4, that would be carbon 5, and that would be carbon 6. That would give us groups at 1 and 5. So really the way we should go is clockwise, right? That's going to give us the smaller numbers. So we wouldn't want to go this way. We would want to number it clockwise in this case. And that would give us really a 1 for the bromine and a 3 for the methyl. And now we really could put it all together like we did before, starting with 1-bromol for the location of where the bromine is at, -3-methyl for the location where the methyl group is at, and the whole thing is cyclohexane. So we'll do the whole name there, cyclohexane. Any questions on that there? So if you have multiple things substituted along a ring here, you do need to give some numbering. Again, alphabetically, you may want to start with the one that should come first in the naming, given it the lower number, and then either clockwise or counterclockwise to whichever one we'll give the other groups the lower numbers. Now, clearly, if we had two of the same groups here, you could start at either of those groups because alphabetically they would both be at the same spot. And again, clockwise or counterclockwise to whichever one would get you the smaller number. Any questions on that name there? Okay. So why don't we do these two? Okay, so looking at this, really just want to count carbons. So we got 1, 2, 3, 4, 5, 6, 7, and 8, and that obviously is the longest chain there. There's nothing else attached, so this should be octate. Here we have 1, 2, 3, 4, 5 carbons. So that is pentane, but it is a ring structure, so that would then be cyclopentane in this case. Yeah. Any questions? Yeah. For the first one, is that what we're talking for B? Yeah, for B, not the condensed formula, but the molecular formula would be, as you said there, C5H10. The condensed formula actually would look just like that, except that you would actually write the carbons in. So it looks something like this, would be the condensed formula for this guy here at the bottom. It would look something like that. So this would be condensed, that would be molecular, and this would be line structure. Yeah. Other questions? And as we talked about, normally when you do line structure, obviously you don't write anything in there unless it's something that's not a carbon. We don't even put the dots and stuff. All right, I think we'll skip these guys. Let's talk a little bit about substitution, which we kind of did. So we kind of jumped a little bit ahead. But a reminder that, you know, we really do go back to the alkanes. When we do add a group that's attached there, we do need to remove a hydrogen to allow it to attach, as we talked about before. But sometimes what can occur is when we're drawing structures, we can make what are referred to as isomers. And isomers are basically the same molecular formula, but different arrangement. And because they have a different arrangement of how everybody is sort of put together, they will end up with some different properties and stuff like that, but they all will have the same sort of connection. So if we look at these two guys here, and whoops, come back. This is 1, 2, 3, 4 carbons in a row. That is butane, and it has C4H10. If we look at this guy, which I'll draw a little bigger, maybe here, CH3, CH3, CH3. This guy has still 1, 2, 3, 4 carbons and still 10 hydrogens. But if we were to apply our naming, like we've been talking about here, when we look at it, the longest continuous carbon chain is 3. You could also get it by going straight and going up in the middle, gives you 3 as well. And 3 here means that the base of this name is not butane, but it actually is propane here, with a methyl group that's attached there at carbon number 1 and 2, and that would be 2-methyl propane. So these are both isomers of each other. They also have some different characteristics because they do have different names. When you're asked to draw isomers, a very big mistake that people make is they decide, well, I need to make it look different. So I'm just going to do that, and it looks very different and not really different, because if we do the longest carbon chain, it is still 1, 2, 3, and down, gives us 4. So that is still butane, even though you drew it kind of different looking to yourself. You know, even if you did and you got creative, like, hey, I'm going to do this to this to this to this, that clearly is going to be something different. It is not. You just drew it that way. because once again, it is 1, 2, 3, and 4. It is still going to be butane. So the best thing to do when you draw isomers or want to know if you did draw an isomer is actually to name it. So if you name the different structures and you come up, I guess the key of that is to name them correctly. So if you name the structures correctly and you come up with different names, then you actually drew isomers of each other. If you come up with the same name, even though it may look different, it's still the same thing. It's just drawn, differently. So why don't we try some here? Why don't you take a moment and draw 3 possible isomers of pentane. The easiest approach would be just to put the 5 carbons straight up. So if I do that, I'm going to fill in my hydrogens to give carbon 4 bonds. That would be pentane straight across. Now, maybe I decide I don't do 5 in a row, but I do maybe 4 in a row and put a carbon up here. I got 3 hydrogens there, 1 there, 3 there, 2 and 3 here. Maybe I just do 3 carbons in a row. Put a carbon up there, and a carbon down there, that's 5. Putting in my hydrogens here to get carbon to 4. Remember, you fill in with hydrogens to get carbon to 4. So now I have 3 different structures. A good way to know is, did I really draw 3 different structures? So if we do our naming here, longest carbon chain here is 4 with a group off of there. So that is going to be 4, which is butane. And 1, 2 going that way, 1, 2, 3 going that way. The number should be 2, right? That's the smallest number. So that would be 2-methyl butane. So that definitely is different than pentane. So those are definitely isomers of each other. Longest carbon chain here in the middle, 3. Really, no matter which way you go, you get 3. We also have a couple of groups hanging off of there, right there and right there. So that is 2 methyl groups, which is dimethyl. Longest carbon chain is propane. And those guys are located at carbon 1, carbon 2, and carbon 3 here. No matter which way you go, they are located at carbon number 2 in this case. That would give me 2, 2 dash dimethyl propane, which once again is a different name, which means that is also an isomer in this particular case. What happens if I had this? Is this another isomer different than the ones that are up there already? Yes. Is that because it looks different? So if we had to go name this, longest carbon chain would be how many? It would be 4. I know it's blank. It would be 4. So it would be 4 right here, which once again is butane. And we have a methyl group that should be at carbon number 2. It is the same as the one above, just drawn backwards. Yeah. So even though it may look different, it is not different, because when we go to name it, you will end up with the same name as for both of those, which means it's the same thing. So it is a very common mistake. Again, people just draw it or turn things around and go, looks different, looks good. So the real way to kind of make sure you got a isomer is to really name it. So once again, the guy here on the bottom would be the same as above, which means it is an isomer, but it's not an additional isomer. So that would be the same as the guy above. Any questions on isomers there? Okay. All right, so we sort of talked about some of these guys here. Our alkyl groups that end in the YL, which are carbon-based groups that are attached. And then our halogens are fluoro, chloro, bromo, and iodo for iodine. Here's a table of some common groups that are attached. This is a methyl group, has 1 carbon. Ethyl group has 2. Propyl, butyl, isobutyl. So these 2 names here are sort of historical names. I would say we do come across isopropyl a lot still. So you should look at that and kind of know isopropyl, because it really does sort of pop up very often as a group. Now, what is the difference between, say, an isopropyl and a regular propyl group? It is really the addition of where it attaches to the main chain. So, for example, if we look at carbons, so let's just take a step back and talk a little bit about carbons. When we talk about carbons, you could actually classify carbons as primary carbon, secondary carbon, or a tertiary carbon. And what that basically means is whatever carbon you're looking at, it's how many carbons are directly attached to it. So a primary carbon would have a carbon that is directly attached to another carbon. So that would be a primary carbon, this guy in the box. A secondary carbon would have a carbon that is directly attached to 2 other carbons, and that would be a secondary carbon, the guy in the box. And a tertiary carbon would be a carbon that is directly attached to 3 other carbons, and that would be the carbon in the box. I personally count carbons. Some people count hydrogens, but carbons I think is the easier move. So if you look at the carbon you're looking at, however many carbons are directly attached to it will tell you if it's a primary carbon, secondary carbon, or a tertiary carbon. So why is that important? If we look at something like propane, which is this, we can attach propane at either end, either left end or the right end here, and we would be taking a hydrogen off of one of those carbons at the end. The carbon at the end, either end, is what type of carbon? A primary, secondary, or tertiary carbon? It is a primary carbon. This carbon is directly attached to one other carbon, which makes it a primary carbon here. This is directly attached to that carbon right there. And that would make this guy a primary carbon. By the way, the guy at the other end is the exact same thing. The guy at the left end is also a primary carbon. It is directly attached to also the guy that is highlighted there in the middle. So if we remove a hydrogen from the primary carbon, that is where it is going to attach. I'll put a circle. It's going to attach to the main chain there through the primary carbon on either side. And that gives us a regular old run-of-the-mill, what is sometimes referred to as just a propyl group. Now, if I decided that I wanted to attach this guy through the carbon in the middle, which is highlighted here, the highlighted carbon is what type of carbon? It is a secondary carbon. The carbon that is highlighted in the middle here, yellow, is attached to the carbon right there, which is 1, and attached to this carbon, which is 2, and that would be a secondary carbon. So if the attachment happens at this secondary carbon, we actually get the attachment to the longest carbon chain via here. And this is how we get what is known as isopropyl alcohol. Not alcohol, but isopropyl group. I may need some of that later. That's isopropyl rubbing alcohol. That's isopropyl. Hold the alcohol for a bit. That is isopropyl, and it would be attached there through the secondary carbon. So because it's attached to the secondary carbon, it has this historical name. It's also used to also be called propyl because it's the secondary carbon where it's attached. You also will sometimes see that with butyl groups. They have one that's known as T-butyl. And that would be what this guy is sometimes referred to as well, because this carbon where it attaches is a 1, 2, and tertiary carbon. So sometimes referred to as T-butyl for tertiary butyl, as to where the attachment happens. So we can't classify carbons based on how many carbons are directly attached to it. And it also can give rise to some special groups. For us, I would say isopropyl is the only sort of special naming group that you should be familiar with and recognize. And then everything else will probably be either a regular sort of group based off of the alkanes or our halogens that are there as well. Any questions on that there? So since we have talked a little bit about naming, obviously, first off, let's talk a little bit about going the opposite way, which is actually drawing the formula from a name. So let's just make up something like we'll go with 2-bromyl 4-ethyl, and we'll go with hexane here. Why not? So let's get this guy here. Let's say we actually wanted to draw this guy. So it's really important when you want to go draw something, the structure, and you're given the name. I personally, like I might have said before, think it's sort of the easiest thing to do because, frankly, they tell you what to draw. You should always, when you have the name and want to draw it, you should always work backwards through the name. So that's always the direction that you should work when you want to draw something like this. So for example, if I want to draw this, I'm going to start with the back part of the name, which is hexane. And remember that the back part of the name is pretty much what tells us how many carbons we need. So hexane is 6. So that is what I should start with, just the carbons, nothing else. Gotta spread it out this way. 1, 2, 3, 4, 5, 6. So frankly, that takes care of that part of the name. What is left in terms of the name are the two groups. And 2-bromo means at carbon number 2, there's a bromine. And 4-ethyl means at carbon number 4, there's an ethyl. Since you are drawing it, you do have the option to either number the carbons 1 and go this way, 2, 3, 4, 5, 6. Or if you wanted to, you could start it the other way and go that way, 1, 2, 3, 4, 5, 6. I personally am going to call this very first one for me carbon number 1, which means I'm numbering this way, right, left to right in terms of numbering. That means that carbon number 4, which for me would be right about here, there's an ethyl group, which is a 2-carbon group, basically. So I could put that in there. At carbon number 2, because I went left to right, I would have a bromine right there. And now I'm out of name at this point. So what is left is everything else is hydrogen. And again, everything else is hydrogen to get to 4 bonds. So if we look at the guy at the far right here, he has 1 line coming in, which means to get the 4, he needs 3 hydrogens. The guy next to him actually has 2 lines, 1 on each side, which means he needs 2 hydrogens. The guy next to him as well has 2 lines, which means he needs, actually has 3 lines if you come that way, which means he needs 1 hydrogen there. We could actually go down to our group too. If you didn't put your hydrogens there, this guy has 2 lines, which means he needs 2. And this guy at the end has 1 line, which means he needs 3. Continuing on to this guy here, 1 and 2, which means he needs 2. The guy with the bromine has 1, 2, and 3, which means he needs 1 hydrogen. And the guy at the far end will need 3. This would then be the correct condensed formula. Yeah. Any questions on that? The expanded formula will look exactly like this, except that you would draw lines out to each hydrogen. So you would include each bond to the hydrogen. The line structure here would look something like this. 1, 2, 3, 4, 5, 6. We got carbon number 2, a bromine. And a carbon number 4 there, which would be 1, 2, 3, and 4. We would have a 2-carbon group right there. Yeah, so that would look something like that if you drew the line structure. Any questions on that there? Okay, so again, going backwards for the name, it's always the way you want to do it. You want to kind of draw just the base structure of it, wait for the hydrogens to the end, and just fill everybody in until they get forward to with hydrogens. Any questions on how to do that there? All right, then let's try some here. We talked about that. So why don't you draw the condensed structure for 3-bromo, 1-butane. Let's also do let's do methyl cyclopentane. Let's do 4-propyl pentane. Chloral methyl heptane. All right, so see what you come up with. Draw the condensed formulas for each of these here. And if you want, do the line structure, like it says. Why not? We'll do both. Do the line structure and the condensed. Okay, let's take a look and see how you're doing. So we'll start here. So again, we're always going to work backwards here. So butane tells us we should start with 4 carbons. Again, I'm just going to draw the carbons, nothing else. That takes care of the butane part of the name. What's left is really the groups that are attached. So 1-chloro means that carbon number 1, there's a chlorine. 3-bromo means a carbon number 3, there's a bromine. I am again going to call this for me carbon number 1, which means I'm going to the right in terms of my numbering. So since that is carbon number 1, there actually is a chlorine there. And going 3 from there would put where we would have our bromine in this case. And that takes care really of all the name. What's left again will be hydrogen to get carbon to 4. Guy at the end has 1 line, which means it needs 3 hydrogens. Guy here next to it actually has 3 lines going to it, which means it just needs 1 more hydrogen to get the 4. Guy next to it on the left here needs 2. And the guy at the end here actually has 2 lines coming in. So it needs 2 in this case. And that would be our condensed formula. Obviously, if you numbered right to left, yours would look the same, just turned around, basically. Yeah. Any questions? Yeah. You mean the chlorine and the bromine? Yeah, it doesn't matter if you drew it up, down. The guy at the end doesn't matter really if you drew it to the left either. So you can do it anyway, as long as it's on that correct carbon. Other questions on that? The line structure would be, you could do it the same way, just start with the 4 carbons, which would look something like that. And once again, I'm going to call this guy, I'll put a circle at it, carbon number 1 there. So off of that should be a chlorine. And then over to carbon number 3 would be our bromine here. And it would look something like that without the little dot at the end there usually. Any questions on that there? All right, so starting this way here, we have cyclopentane. So cyclopentane tells us it's 5 carbons, but the cyclo part tells us it is a ring structure. So we will have 1, 2, 3, 4, and 5. And once again here, that takes care of that. Methyl with no number means there's only 1 methyl group attached. So frankly, you could put it on any carbon you like in this case. So I'm just going to go here since I don't got room above. And I'm just going to put my methyl group right there. At this point, we just need to add our hydrogens. So this guy should have 2. This guy actually should have 1. This guy should have 2. This guy should have 2. And that guy should have 2. Any questions on that one there? The line structure would look just like that without anything written. Look something like that. Any questions on that one there? We'll go here next. Going backwards is pentane. So that's going to be a 5-carbon run. And we'll go 5. 1, 2, 3, 4, and 5. 4 propyl means that carbon number 4. So once again, I'm going to call this carbon 1 for me, which means my carbon 4 is over here, and propyl is 3 carbons. I'll get that right. So again, if you want, you can put the hydrogens now, but or you can wait till the end. That takes care of that, and now everything else is hydrogen. Guy at the end needs 3 to get the 4. Guy here needs 1. Coming down, there's 2 lines, which means it needs 2. There's 2 lines, it needs 2. There's 1 line, it needs 3. 2 lines needs 2. 2 lines needs 2. And 1 line needs 3. So it looks something like that there. Again, if you were going to do the line structure, you would do the same thing. You would start with your 5, 1, 2, 3, 4, and 5. And at carbon number 4, which would be here, we have 1, 2, 3, and 4 coming off of it there. It would be something like that in that case, yeah. Any questions? Yeah. Propyl it is 3, and I drew like way too many there. That would be a butyl group I drew there. Thank you. Was just again just making sure you're paying attention over there. I got it right here. I mean, come on, it's like just a little wrong. No, I'm just kidding. There you go. How about that? Better. There you go. Still wrong, they say in the business, right? That's right. The guy cuts off the wrong arm. Oh, we were supposed to cut off the right arm. Oh, it's just a little off, right? It's all right. All right, so that would look better. Thank you. It should be 3, obviously, on that one. Thanks. Other questions on that there? All right. So lastly here, heptane. We're going to do 7. And I'm going to regret it right now, but we'll do right about here. So I'm going to make a little room up here for my 7, I think. All right. All right. So heptane is 7 here. Here we go. Let's try that here. 1, 2, 3, 4, 5, 6, and 7. I think I got that one. That's good. Once again, I'm going to go carbon 1 right about there. That means that carbon number 5, which should be 1, 2, 3, 4, and 5. I have a methyl group. Takes care of that. And at carbon number 3, 1, 2, 3, I have a chloral group, which takes care of that. Now we're going to put our hydrogens in. So 3, 2, 1, 2, 1, 2, and 3. Any questions on that one there? All right, I'm going to attempt it. Here we go. Keep me honest. So 1, 2, 3, 4, 5, 6, and 7. I hope 1, 2, 3, 4, 5, 6, 7. So at carbon number 3, which would be here, I'm just going to draw it up because there's something below it. So we'll go that way. And we then at carbon number 5, which should be here, I'll also draw it up. You could draw it down. I'm just going to draw it up because there's writing in the way. But you could draw both of those down at those points. Any questions on how to go from name to formula here? Okay. So clearly you need to be able to go both ways. Name to formula and formula to name. Any questions on any of those there? Okay. All right, so let's do a couple of naming here to end it on this part of the naming parts. So let us do, yeah, I don't know what I'm drawing. Let's do that. All right, give names for these guys here. Which will give us the base of the name. Then obviously we have a group hanging off of there. So 5 carbons means that the base of our name there should be pentane. This group would be attached numbering 1, 2, 3, 4, 5. Obviously, if you went the other way, 1, 2, 3, 4, which is a much larger number. So 2 would be the way that you would want a number. So that would be a chloral group at number 2, and that would give us something like 2-chloral pentane. Any questions on that name there? Coming to the one on the bottom, looking for the longest continuous carbon chain, 1, 2, 3, 4, and 5. I think 5 is the winner. You could actually get it a couple different ways. You could go from the bottom here up 1, 2, 3, 4, and 5 as well. But if you have a straight one, you might as well just take the straightest one. Makes it sometimes easier to see maybe everything else that is attached there. In this case, we do have 1, 2, 3, 4, 5 carbons as well, which would be the base there, pentane. This line with nothing attached means that there's a carbon at the end and 3 hydrogens, which means it's a methyl group, and the same thing here. That is a methyl group as well. So again, in line structure, if there's just a line, nothing attached, it is a methyl group. If there's a line with something attached, they will put something there if it's not a methyl group. So that's 2 methyl groups in a same compound. So that would be a dimethyl situation happening. In terms of numbering, if we went right to left, that would be 1, 2, 3, 4, and 5. That would put the methyls at 3 and 4. If we go left to right, that would be 1, 2, 3, 4, and 5. That would put the methyls at carbon 2 and 3. The better way is going this way, right? So it gives those guys the smaller numbers. We do need both numbers here. So we need a 2, 3 dash dimethyl and pentane here at the end. Any question on that name there? Again, a comma between 2 numbers, and again, the dash between a number and a letter. Any questions on that one? Lastly, here we got a little cycloalkane action happening here in the triangle. We also have a chlorine and again a methyl group that is off of it. So that's a methyl, that is a chloral, and the base of our name is cyclopropane. In this case, we do need to number, and I probably should start numbering at which group? The chlorine, because alphabetically that should probably come first. So that's going to be a 1, and then the proper way in this case actually would be counterclockwise. That would get us to a 2. If we went clockwise, that would be a 3, which would be a larger number. So this would be a little 1 chloral, 2 methyl. See if I could join them up. Not bad. Cyclopropane in this case. Yeah. Any question on any of those names there? All right. So obviously, like I said before, you need to be able to name these things, you know, the group names and all that kind of stuff. So just to finish up on some of these properties of alkanes, again, are nonpolar, as we talked about before. They're also sometimes referred to as hydrocarbons. A lot of them that just have carbons and hydrogens. The first several of them are gases, like methane, ethane, propane, butane. And again, that's really because they're held together by really weak intermolecular forces. So they're able to go into the gas phase really well or easily. Pentane, hexane, heptane, octane. They're also highly volatile, highly whatever it says there. Highly volatile means that it will go into the gas phase really easy. So again, you open it up and it will just go into the gas phase. I don't know what the other word means, I said, but that's what that means. A lot of really long alkanes are what makes up fuel, and that's how they get fuel. They take it and they do what is referred to as cracking. They basically break a really long chain of carbons up into smaller ones like octane, you know, like you put in your car, and they break the big chain up into those small ones. Little larger things gives us other organic things like wax and things of that nature. Obviously, they're non-polar, as we talked about. They're insoluble in water because water is polar and they cannot hydrogen bond really well with water. They're usually less dense than water, which means when they separate out, you usually will find the organic guy up on the top layer, and the water layer is usually the bottom. And a lot of them are flammable in air. A couple important reactions that alkanes undergo. One we talked about before is a combustion reaction. So a organic combustion reaction is basically this organic guy plus O2, and you always get CO2 and water. Is a very common reaction that alkanes undergo. They also undergo what is referred to as substitution reactions. And there's really a few different types of reactions in organic chemistry: substitution, addition, and elimination reactions. In a substitution reaction, it is pretty much what it sounds like. Something gets substituted. So something comes in and something comes out, basically. So in an alkane, if you have something, say, like this guy here, it's a bunch of hydrogens. All of these hydrogens are what are referred to as being equivalent. They're all basically the same. No matter what hydrogen you pick, they're pretty much the same. So if you took an alkane and you reacted, say, with Cl2, for example, maybe a little energy there or light to help it along. What's going to happen in this reaction is one of the chlorines will come in and one of the hydrogens will come off. So basically, that's the substitution part. Hydrogen comes off, the halogen comes in. And when it does that, what happens in this reaction is, frankly, absolutely everything stays the same, except you just take the hydrogen off and put the chlorine in its place. So if you were to draw this, it looks exactly the same. Nothing changes. You could draw it really quickly and just simply put the chlorine there at the end where you took the hydrogen off. By the way, when the hydrogen comes off, there's also an extra chlorine hanging out, which means those two will come together, H plus and Cl minus, and you'll make some HCl in this case as well. But the main organic product would be this guy. It's basically an alkane that you substituted on a halogen. That would be chloroethane in this case, in this particular case here. So in a substitution reaction, pretty much hydrogen goes off and the halogen goes on. Yeah. So everything else stays the same. It doesn't matter if it is like a ring type situation here. There technically is a hydrogen at two hydrogens at each of those carbons. So the exact same thing happens. Hydrogen comes off and a chlorine comes in. So you would end up with exactly the same thing, except that you would have a chlorine in the place of a hydrogen. Everything else would look the same. You would also, again, get the HCl in this case. This is what is referred to as usually being mono-substituted. And usually if you have this reaction, that's usually the product they want you to draw. It's just the mono-substituted one. Under the right conditions, you could get all the hydrogens basically to pop off and pop on all the chlorines all the way around. So usually you just draw what is referred to as the mono-substituted one. So those are the two major reactions that alkanes undergo: combustion and a substitution reaction. And the key was we start drawing some of these reactions is people like to make all kinds of weird things. Like, I want to think the entire thing changes, and it really doesn't change. There's only really one part of the molecule that changes. So for example, people, when they see this, could decide, well, it's chemistry, so I should just open that thing up out of the ring because it looks more chemistry like, and it's not really is not what happens. So keep that in mind as we go through different reactions. There's pretty only one part of the molecule that changes. Everything else stays the same, which makes it really easy to sort of figure out what you should end up with. All right, so here's an example of butane and some other ones here. These are all combustion reactions, CO2 and water. Any questions on alkanes here? All right, we're going to then talk a little here about alkenes and alkynes. These are the next two sort of organic groups. Alkenes have the functional group of the carbon-carbon double bond. So there's got to be at least a carbon-carbon double bond. And the alkyne has the functional group of a carbon-carbon triple bond. So If there's a triple bond in there, that's an alkyne. If there's a double bond, it's an alkene. And if they're all single bonds, it's an alkane. So these are different classes of organic compounds. The good news is they're pretty much all named based off of those alkane names. These are what are considered unsaturated. So we talked about saturated hydrocarbons. So for example, if we took this guy here, which is our 2-carbon guy with all single bonds, that is ethane. This is saturated. Remember that saturated means it has the maximum number of hydrogens it should have, and each carbon has a maximum number of hydrogens here. If we lay up a double bond here that's going on, we will end up with something like this. Now, to make that double bond, you also see that we sacrifice basically a hydrogen on each carbon to do so. And we get what is known as ethene, E-N-E, as that's an alkene. This is an unsaturated because each of those carbons don't have the maximum number of hydrogens. They're missing one, basically, to make the double bond. If I make a triple bond, I once again will sacrifice a couple of hydrogens to make that bond. And this is what is known as ethyne, Y-N-E, also unsaturated. This is an alkane, and an A-N-E. This is an alkene, ends in E-N-E, and this is an alkyne, ends in Y-N-E. So they're all based off of those alkane names. You just change the ending part to fit the functional group, and you pretty much have your name as you go through it. Again, they're unsaturated here because they have a double bond or a triple bond, and they're missing the number of hydrogens. Alkenes have a general formula of CnH2n. Alkynes have a general formula of CnH2n minus 2. And that's what we see here. This guy has 2 carbons and 4 hydrogens. So CnH2n. This guy here below it has 2 carbons and 2 hydrogens. 2 times 2 is 4, minus 2 is 2 hydrogens that is left over. Again, we sacrifice those 2 hydrogens every time we drop a double bond in there. Any question on that there? No? So again, we can identify alkenes by that double bond. It also affects the geometry of it. This guy has 1, 2, 3 electron pairs and 3 bonds, which means it does not have the tetrahedral geometry like our alkanes. It has our trigonal planar geometry, which is our triangle geometry here. Looks like a triangle basically at each end. So these guys will make that triangle geometry because of its double bond. Alkynes have that triple bond, which also affects its geometry. This guy has basically, whoops, down here, this guy. This carbon has 2 electron pairs and 2 bonds, which gives it its linear geometry, so the straight line. So basically, as you can see here, it ends up being a straight line all the way across because of the triple bond. So again, it does change the geometry of these molecules if you have a double bond versus a triple bond versus a single bond. Again, our single bonds has the tetrahedral geometry, which gives you that kind of zigzag shape. Double bond, again, more of a triangle type shape. And obviously, our triple bond will have a linear shape. Any questions on that there? So let's talk a little bit about naming these guys. The nice thing about naming these guys is it's pretty much the same thing. The difference is, though, the double bond and the triple bond get the priority in terms of numbering. So the priority here shifts from the groups to the double bond or the triple bond when you number it. The other difference is you need to give the location of the double or triple bond. So you actually have to give the location of the double bond or triple bond. And once again, it does take the priority. So you want to give it the smaller number when you are doing that. So let's take a look at this guy here and see how this works. First off, we have 1, 2, 3, 4, 5, 6, 7, and 8. So in this case, 8 carbons is based off of octane. There is a double bond in this case, which means it goes from octane to octene, E-N-E. Now, we do need to give the location of where the double bond is located. So we'd still have 2 ways we could number this. We could go left to right, which means this would be carbon 1. This would be carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7, carbon 8. We could also obviously go the other way, where this would be carbon 1. This would be carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7, and carbon 8. Which way gives the double bond the smaller number? Yeah, we want to go this way. The priority here is the double bond, regardless if there's things attached to it, groups. It is the double bond that gets the priority, which means that this would be what is known as 3-octene. The 3 is the location of where the double bond is at. So that's what that 3 means. So that would be 3-octene in this case. Any questions on that name there? Now, if we look at the one on the bottom, we would do the same thing. The longest continuous carbon chain that includes the triple bond in this case would be 1, 2, 3, 4, 5, 6, 7, 8. I'll learn counting soon. It'll be okay. 1, 2, 3, 4, 5, 6, 7. So if we want straight and then down, I think we only got 7 in that case. 1, 2, 3, 4, 5, 6, and 7 if we went that way. We could not go this way. 1, 2, 3, 4, 5, 6, 7, 8. The reason we could not go this way is because we missed the triple bond. So the longest carbon chain needs to have the functional group in it, and that would avoid the functional group, which you can't do. So when you are counting the longest continuous carbon chain, it does need to include the functional group. You can't run away from it. So now let me just try this one more time here. There we go. All right. One more time with filling here. Here we go. 1, 2, 3, 4, 5, 6, 7, and 8. Looks like a winner there, I think, in terms of longest carbon chain. Yes, ma'am. So there's a carbon here. There's a carbon here. So because this triple bond is linear, right, which is why it's flat right there. So there's a carbon there and there. Then there's a carbon there, carbon there, carbon there, carbon there, carbon there, and carbon there. Yeah. That's okay. I've missed it many of the lectures. I went right by it a lot of times. That's right. And that's why also if we kind of went straight and down, we would only have 7, 1, 2, 3, 4, 5, 6, 7. And again, going the other way, as we talked about, would avoid the triple bond, which you can't do. So that is 8 carbons still, I think, which has a triple bond. So instead of octane, it would be octene, Y-N-E. We then would want to give the triple bond the priority in terms of numbering, which means we definitely should number this way, right? 1, 2, 3, 4, 5, 6, 7, and 8. This would then be 1-octyne. The 1 is for where the triple bond is located. I still have a group that's attached, right? And my group is here, Now, because I locked my numbering in going this way, I have to keep it for the group. That means the group would be at carbon number, it would be at carbon number 4, and that group would be what we got there, 1, 2, and 3, I believe, hanging off of there. So this carbon is obviously part of the main chain, so it's not the group. So we would start counting here at this carbon. And that would be 3, which would be propyl, I think, not butyl. So that would be 4 propyl, 1 octine would be the name here. Any questions on that there? Yeah. I'm sorry, say it one more time. The bottom one, this group down here, it would be a propyl group because there's 3 carbons. Yeah. So basically it's this part of it. We wouldn't count if the question is, why don't we count that carbon there? We don't count that carbon because it is already counted in the longest carbon chain. So it's part of the main carbon chain. So basically what you have there is that carbon, which is part of the biggest carbon chain. And then really the lines coming down to your 3 carbon group that's attached. And that's really the group that's attached is that 3 carbon group, which would be the propyl group. Yeah.
You were saying how it's alphabetically divergent and sometimes the numbers. So it doesn't matter if octane goes or
It does not. So this wouldn't be alphabetical because this is the main part of the chain. The alphabetical would be the groups. And to answer your question, the answer is still yes. That even if you had 2 groups where alphabetically, say the guy with an A or something, or a B would come first, but it has like a 5 versus the next guy, which has a 3, you would do 5 dash the guy with the B, 3 dash the guy with the A. So it's alphabetical based solely on the name of the group, regardless if there's a prefix or regardless if there's the numbering order, you put it alphabetically. Other questions? Now, there are certain things that do not need the number for the double bond or triple bond. And those are guys where it does not make a difference. So just really quickly to finish up here, if we had this right here, if this was our double bond, it doesn't really matter sort of where it's at. You don't really, actually, this is a bad example. Let's do that one there. Let's do that. Let's just do this example here because it does matter. So in this case, if this was our double bond, there's only really one place where it could be. It's either going to be at this carbon, which is 1, or that carbon, which is 1. And that's why something like this would just be called ethene. You don't need to give the location because it's the same location no matter how you would number it. So usually around 3 or more carbons, you do have to give